If any question, just feel free to ask me. All right, so today we are going to continue with our lesson. So I have taken some few questions in previous question papers. Maybe some of the questions you have already seen them. And then secondly, there are some things that I'm gonna have to let you know them, because those things that I'm gonna have to let you know them, they will come in your exam. Normally they will ask such questions in order for you to prove them. So just in case, as I've indicated before, real analysis is about proving. So anything, they can ask you anything about proofs, and in your exam, they will make sure that at least you have one proof, that you have to have at least a question to prove a theorem. So I'm gonna also show you that how to work on that. So the first thing that I'm going to talk about, we're gonna do the questions that I'm going to be dealing with. I'm gonna tell you where to find this question in your question papers, but the way I've answered them, it won't be exactly the same way as in your memos. I'm answering them based on how you're supposed to do it, and then also give you understanding, so that if you can get any question that is not the same as question that you have seen before, you must be able to answer it. So as we are going to talk about the sequencing, we are going to discuss about the sequencing. So the first thing that I'm gonna do now, I'm going to give you an example of a sequencing. So when I give you this example of a sequencing, we're going to work it out. Then I'm gonna explain to you each and every step. So this sequence, you might find it in one of your question papers. So the question state as follows. It says limit. Okay, where is my mouth? I can't see it. All right. So the question says limit when n approaches infinity of n squared over 2n squared plus 1 equals to 1 over 2. So when you answer this question here, remember this is a real analysis. So when you answer this question, you don't have to use the method of calculus. So the first thing that you are going to do, always when you see a question based on this, exactly this fashion, always follow this procedure that I'm going to give you. The first thing that you're going to do, you're going to say let be, you can even memorize this because it works to all the questions based on these similar questions. Hello, can you hear me?
Yes, I can't see anything.
Oh, sorry, let me check but I think I did. Okay, can you see? Let me just stop sharing. I'm sharing the whole screen. Oh, let me share sorry. I was just sharing for window. I think now, can you see now?
Yes.
Okay, sorry, yes. So this limit here, if you get any question, like for example, there is a question that we were doing in question number, I think it's question paper for 2020. You remember that first question for the limit? It applies the same method. So the first thing that you do when you answering this, actually it comes as proof this. So our proof, your proof, when you write it, the first thing that we're gonna let any positive, let B, you can say let B any positive, let be any positive, or let there be any positive E. This E, you write it like this, E, or B, let any positive, or let any positive E be given. So this E that we are talking about, this E is called an epsilon. When we say epsilon, we are trying to find an error. It's for error. We are trying to find an error because here, when we are dealing with this mathematics, before I'm gonna recall Newton. Newton was trying to figure out about the convergence of sequences. So he was getting closer to the answer, but there was a little error. Then, as a mathematician or previous mathematician, they end up coming with an answer that, okay, we have to calculate something. There must be an error that this sequence cannot exactly be equals to 1/2. So we must introduce an epsilon to say, no, it can be closer to 2, but there will be some digits that are very, like maybe it can be 1/2, 0.5095, like that. So that's why we introduce this E as an epsilon. So after writing this, let there be, let any positive E be given. Then we will need to find, we have to find a natural number. We must find, you can also write it as we need to find a natural number. Natural number, you can just present it like this, but it must have double cross there. A natural number, so that every term in the sequence, this sequence, remember, it have terms. It can start as a term 1, term 2, until term n. So that every term in a sequence on or after, it can be on or after the nth term, on or after, okay, on or after, and after the nth term is the last term. Nth term is closer to 1/2. The 1/2 that I'm talking about is this one there. Is closer to 1/2 than, we can say 1/2 than E, than an error epsilon that is such that, this one means such that, you can just say s dot t, such that if this epsilon, the absolute value of n squared divided by 2n squared plus 1 minus 1/2 is less than an epsilon whenever our n is greater than n, this n, the term n. So this, some students, sometimes instead of the way I've written it here, you can say let there be E such that, then you eliminate all this such that absolute value of n squared over 2n squared plus 1 minus 1 over 2 is less than epsilon whenever n is greater than n. So this is just a defining, it's a definition in the book. It's just that we are writing it in terms of the sequence that we are given. So it's the definition that there is an absolute, it's the definition that I once gave it to you when it's talking about if there is absolute value of Sn minus n is less than E whenever n is greater than 1. It's just that we are interpreting that definition based on the question that we are answering. Then the moment when you get to this stage here, then now you can simplify, you can now solve what is inside the absolute value. When we solve what is inside the absolute value, we can take the lowest common multiple of the two, which you can find that is going to be 2n squared plus 1. Then if we divide this by this, you're going to see that we're going to get 2n squared minus, if we take this one, is going to be 2n squared minus 1, absolute value, which is less than epsilon. So this one here, you will see that this will cancel with this. Then you are going to remain with, due to space, I'm just gonna just write it like implies that we are going to remain with absolute value of -1 over 2, which you can write it as 4. We're going to write it as 4n. This 2 times 2 here is going to be 4n squared plus 1, which is less than e. So remember, in terms of absolute value, it's the same as, just that some of the steps here, we're going to eliminate them. But because I'm teaching you, I'm going to show you how you do them. So it's the same as, you can say -1, absolute value of -1 over absolute value of 4n squared plus 1, absolute value is less than what? Epsilon. So this can imply that you know that the absolute value of anything that is negative is equals to positive of the answer. So which means this can lead us to say we have 1 over absolute value of 4n squared plus 1, which is less than an epsilon. So now when we have this, we can solve this equation here. If I make a 4 plus n, like if I swap these two here, the 1, if I say absolute value of 4n squared plus, or even if I don't write an absolute value, I can just write this answer like this way. I can just write it as this way. Let me just change here. I can just say, then I'm going to be left with 4n squared plus 1. When I swap these two, then this one here is going to be what? It's going to be 1 over 2. But this sign here is going to change. So it's going to be greater than 1 over epsilon. So now I can just swap this one. I'm going to be left with 4n squared, which is greater than 1 over epsilon minus 1. I can bracket this. Then if I divide everything there by 2, if I divide everything by 4, I'm going to be left with n. I'm going to be left with n, which is greater than 1 over 4, in brackets 1 over epsilon my mouse is moving fast, I can't see it. Okay, all right, yeah, 1 over e minus 1. Then this one here, we can write it as n is greater than 1 over e. Our capital letter N is greater than 1 over e, because remember our n is great equals to what? Is great equals to the small letter n here is great equals to this one, capital letter N. We can write it as n is greater to 1 over e, in brackets 1 over e minus 1, when n is great equals to n. The capital letter N, you can just characterize it as capital letter N. Then now in this step here, if you solve with maths, everything here mathematically, you will find that you are going to have an n which is greater than square root of 1 minus 2 epsilon over 4 epsilon, which is going to be greater than, again, or we can just say equal to 1 over 2. This is just equal sign there, 1 over 2 square root of epsilon. Then when you have written this, when you have this n, which is greater than that, then we can now proceed with the, can I erase here? Or do you have any question before I proceed?
We can proceed.
Okay, so now when we are given here, we can now proceed. In calculus, you were taught about the delta, whereby you will be saying, suppose that a delta with suppose that we have a delta which is equal to the mean maxi of 0 into 1 over 2 square root of epsilon, the one that epsilon, 2 over square root of epsilon. Then after that, we are going to substitute this 1 over 2 square root of epsilon in our main equation. So our main formula there is going to be our epsilon, whereby you get -1 over, we can start at -1 over 4n squared plus 1, which is less than n, and this n here is less than, which is less than, where there is this n here, we are going to substitute 1 over 2. So this 1 over 2 here, remember our n is greater than what? 1 over 2 square root of epsilon. So if we change this to be n, if we make e the subject of the formula, you will find that our e as a subject of the formula here, we can multiply everything by 2. We're going to have 2n. You will have a 2n, which is greater than 1 over 2n, which is greater than 1 over square root of epsilon. And if you take this back, you will see that your 2n is less than 1 over 2n is less than what? Is less than square root of epsilon. And if we take back, you will find that your square root of n is less than square root of, sorry, let me rewrite it properly. So if we take it back, you will find that your square root of 1 over 2n is less than epsilon. So now when you come this side here, you are going to say this is less than square root of 1 over 2n, whereby this one, when you substitute it, you're going to substitute this equation here, this one. Then when you substitute this one, which is equals to square root of 1 over 2, where there is n, you put in brackets 1 over 2 square root of epsilon Then this one, when you calculate, is going to give you exactly E, which is required. So this proves, this exactly every step that I've done there, it proves that this is exactly the proof of limit when n approaches infinity of n squared divided by 2n squared plus 1 equals to 1 over 2. So this is exactly the same process that we are using now. It works to every question that we will have based on the limit, this limit. So now I'm going to give you a theorem that they normally ask it in the exam. You can be asked, they won't really mention that this is a theorem. They are going to tell you that every convergent sequence, they will state that every convergent sequence is bounded. This is the theorem that if you check on one of the question papers, you will find this statement and you will be asked to prove it. Every convergent sequence, okay, let me erase here. Is bounded. So now I will have to define what is convergent sequence and what is divergent sequence. I haven't started proving this statement that every convergent sequence is bounded. So a convergent sequence, if we have a sequence that we can define as Sn, if Sn approaches L when n approaches infinity, then this sequence, we call it is convergent. Convergent sequence is a convergent sequence. But if it's a convergent sequence, but if Sn, our Sn, this is a sequence, then this sequence, it approaches infinity. It can be positive infinity or negative infinity. Whenever our n approaches infinity, then this sequence, we call it divergent. It's a divergent sequence. It does not converge. We call it divergent. It's called divergent sequence. So in sequence that divergent, they converge, we have a sequence that converge absolutely convergent sequence. So absolutely convergent sequence is a sequence that strictly converge to a point whereby if it's 1 over 2, it's going to be 1 over 2 without any form of, with a direct form when we prove it. And we also have a sequence that diverge, that converge, conditionally convergent, is conditionally convergent. So the conditional convergent sequence, it's a sequence that it moves, then after that it converge. So when we say it moves like that, I mean it's a sequence whereby it will be having a condition that this sequence, it might be diverging from, if I'm talking based on an interval, it can be diverging between 0, maybe is less than a, let's say is less than r, which is less than maybe 3. So in this interval here, if this sequence converge, it means that this sequence is conditionally convergent. So which means there is a point, some numbers, or there is a point in this sequence whereby this sequence, it does not diverge. So this one, we call it conditional divergent. So now we're going to go to our proof. So now when we prove this sequence, that statement of every convergent sequence is bounded. So remember, I have already taught you about what is bounded. There is a sequence that is bounded above, and there is a sequence that it can be bounded below. So the sequence that can be bounded, that is bounded above, it have an upper bound, and a sequence that is bounded below, it have a lower bound. So which means the sequence that is bounded above, it have supremum, and the sequence that is bounded below, it have infimum. So now, when we prove this, we're gonna say, suppose that Sn, this is a sequence approaches L, then for every number, E greater than 0, there is an integer n such that absolute value of Sn minus L is less than epsilon whenever our n is great equals to n. In particular, we can let our E equals to 1. Then if we let our E equals to 1, we can find n such that we can find our n such that this absolute value of n, absolute of Sn minus L, is going to be less than 1 whenever n is greater than or equals to n, capital letter N. Then for when we use this, we can use the triangular inequalities. When we use triangular inequalities, if we solve, for example, if we say absolute value of Sn, our absolute value of Sn, it can be equals to absolute value of Sn plus minus L plus L, which this one can be less equals to, according to triangular inequalities, less equals to Sn minus L plus absolute value of L. And remember, our Sn minus L is less than what? Is less than 1. So this can be less than 1 plus absolute value of L. For every n greater than or equals to n. So the number L, this is, remember this L is a number. So the number 1 plus L, absolute value of L, could be an upper bound. It could be an upper bound, could be an upper bound, could be an upper bound for all numbers. It could be an upper bound for all numbers of absolute value of Sn. Remember, here we are dealing with a sequence. This sequence, sometimes in your textbook or in the exam, They might not give you Sn. They might give you a sequence, maybe 1/2, then comma 1/4 like that. So you have to first generate the general formula for that sequence, then you solve it. So now when you have this, thus we can now say thus, you can just say thus there is an M. You can say there will be an M, but don't use the same letter as this letter we are using. You can use maybe a letter M, so that this M, it can be equals to the maximum of the sequence, which is can be S1, S2, until these are going to be an absolute value of absolute value of S n minus 1, and the upper bound, remember, is the last one, which means you're going to say 1 plus absolute value of L. So after that, when you have done this, we must have, you will have, let me just delete here, you will see it in the video. Then we will have our absolute value of X Sn is less than what? Is less than M. That's equals to M. For every value, for every N. Thus, one plus absolute value of L, but this one statement, you don't really have to write it, but if you want to, you can write it. You say that's 1 plus absolute value of Sn is an upper bound. So this just conclude our proofs for that statement. This is how you prove it. Exactly the way I did. If you find that statement, just remember that that's how you prove it. So now we're gonna do some few questions. So in these questions here, we're going to deal with some of these questions that I'm going to be doing. They are in your question paper. They are about the sequence that diverges and sequence that converges, and also the
Which question paper?
So if you check the way I'm going to answer these questions, they won't be the same as in your memos. I'm going to give you a clear understanding. So if you go to your, I think question exam paper for 2020, it's written December, the one we were dealing with, you will have a question on question 3. You will have a question which states that for each of the, like it says, it states as for each of the following definition, if sequence is absolutely convergent and conditional, or state each of the following determine if the series is absolutely convergent, conditional, convergent, and divergent. So the first one that were given there, it was A. It's you are given number A. You are given a series whereby is sum of R equals to 1, infinity, in brackets, minus 1.
Which question paper is this?
Check question paper 2020, December 2020, or October, November, December 2020. The one with that sequence. You remember the question we used to do in question number 2? Did you get it?
Yes, I found it.
Okay, so it says like we have to determine if this series is absolutely convergent, conditional convergent, and divergent. So I already explained to you what is conditional convergent and conditional convergent, and I also explained to you what is absolutely convergent and also what is divergent. So now when we are given this series, the first thing that I'm going to talk about is minus 1 to the power r. So minus 1 to the power r, if we start at 1, you will see that your sequence is going to be negative, positive, negative, positive. So this part here, because we know that it's going to be changing only between negative, positive, we are not going to take into account that much. So we are going to take into account r to the power 4 over factorial of r. So now when we take into factorial of r, remember the factorial of r, if you have 3 factorial of r, this is the same as 3 times 2 times 1, and which I can factorize as 3 times 2 factorial of r, which it can be the same as 3 if we have n factorial of r. Then if you have n factorial of r, remember that you can work it as n multiplied by is n minus 1 factorial of r. So what if I have a factorial of n plus 1? This can be n plus 1 multiplied by, we subtract again, n minus plus 1 multiplied by n plus 1 minus 1, plus 1 minus 1 factorial, which it can be n plus 1 in brackets n factorial. You see that? So this one I'm just stating them so that you can follow when I'm answering this question. So let's go straight to the question. So this is our question. So we're going to let our a, we're going to let our an equals to n, because here we are using n, here that we're using r. We're going to substitute where there is r, we're going to substitute with n to the power 4 over n factorial. And we can let our alpha, just to make them different, alpha n equals to alpha, you can just say a n plus 1 over a n. So since our alpha n, which is equals to, we can say since limit, let me just say since limit when n approaches infinity of alpha n is equals to limit when n approaches infinity of, where there is alpha n, we're going to put n plus 1 in this equation here. Then we're going to have n plus 1 to the power 4 divide by, we put everything there, is going to be still n plus 1 factorial over n, an here, where there is this an, we put exactly this, is just going to be n to the power 4 over n factorial. So now after this step, if you make your calculation properly, if you just divide it, you will find that your answer is going to be if you work this properly, is going to give you limit when n approaches infinity of n plus 1 to the power 4 n factorial over n plus 1 to the power n to the power 4. So now, based on this here, you can see that if we say n plus 1 factorial is going to be equals to what? The n factorial. You see that I proven to you that. Then we can just check that, okay, our equals to, you can just say now limit when n approaches infinity of this part here, we can take only 1 is going to be equals to this part. Then we're going to have 1, we're going to have n plus 3, 1 to the power 3, because I've taken plus 1 so that it can be equals to this part over this part there is going to be cancelled with the others there. Then we're going to be left with, n to the power 4 only. Do you understand this step that I just did now? Or should I explain it further to you?
Can you explain it again?
Okay, so what is happening there is that, remember here is n plus 1 to the power 4 into n factorial. So I'm going to take n plus 1 to the power 3. And then I have n plus 1 to the power n factorial. So this part only, according to this one, you can see that n plus 1 factorial equals to this part. So if we substitute back here, we can end up having n plus 1 to the power 3 equals to what? N. This part equals to n plus 1 factorial. So this part will cancel with this part here. You see that one. Then that's why we're going to end up with n plus 1 to the power 3 over n to the power 4. Do you understand it now?
Yes, I understand.
All right. So it's just that here in this second year, they assume that many steps you know them when they are teaching you or when they are writing the memos. So now when you're left with this step, so what we can do now, we can take out, this is just the method of factorizing. I'm just trying to simplify my life. I can just say this is the same as limit when n approaches infinity of, I can take out 1 there, 1 over 2. If I take 1 over 2, 1 over n, sorry, I'm going to be left with n plus 1 over n to the power 3. This is also to the power 3, which this I can write it as limit when n approaches infinity of 1 over n in brackets n plus 1 over n to the power 3. It's just the method of factorizing. So now we know that the limit, remember, limit, I have told you this already, when n approaches infinity of 1 over n equals to what? Equals to 0. Then we can use the laws of limits. It allows us that we can say limit when n approaches 1 over 2 over n, sorry, dot limit when n approaches infinity of n plus 1 over n to the power 3. So inside here, remember our n